Okay.
Yeah.
Looks good.
Yeah. 2 minutes, right? We'll wait for 2.
Ram, for the registration, we just get the names and ask Angela to register them, that's all.
Oh, okay.
Yeah, because otherwise it's gonna take forever. Like, I mean, whoever wants to come, just get the name and she will register them.
Okay.
I have one question. I think the computer station is acting like a switch, like tap. You
Yeah,
said
correct.
some flow into tap.
Yeah, yeah.
We are closing tap. It looks like switch off and fully on.
Yes.
Like turn on.
Turn on and turn off.
Why do they developing the DC circuit breaker instead of the converter control?
Why do
Well,
you do this?
why? Because if you have more than one DC line, if you have more like a DC grid, if there is a problem with one converter, so you have to bring the whole system down. Yeah. So if you have a DC circuit breaker, you can isolate that one converter and then run the other converters still. That's why DC circuit breaker is needed when you have more than 2 terminals. Yeah, with the 2 terminals, you don't need one because you can use AC side breakers to open the, you can use the converter control to control the current, and then you can use the AC side breakers to open the whole station, converter station. But if you have more than 2 converter stations, like a DC mesh, that is where. I mean, if you don't have DC circuit breakers, you have to bring all 3 terminals, 4 terminals down. The whole system goes down, the DC network. So you don't want that. So that's why you want DC breakers. Yeah. You're welcome. Okay. Okay, let's start again. The next presentation is on basics of corona and comparison of AC versus DC. My colleague, Mr. John Chen, has another presentation on electrical effects. I think he's talking tomorrow first thing in the morning. He will have more details on this subject, more practical things. I'm just going to give you a brief overview on the physics, how corona happens, why we need to worry about this, and some of the basic information in the next few slides based on some books that are written by one of the experts, Dr. Sharma Marwada, who did a lot of work at Hydro-Quebec. So this, again, fundamentals, basics, I'm going to discuss very briefly here, and more information will follow tomorrow morning. So that will help you, understand more about it. Okay, so what is corona means? Let's start with that. Some of you might be aware of this, but some of you may not. First thing is, why do we even need to worry about this term called corona? When you are designing lines, transmission lines, high voltage AC and DC lines, there are 3 things that you need to worry about is air insulation. Air insulation means you have an overhead conductor, you have a ground, the air in between is the air insulation, right? So that is the air that is sitting from the conductor all the way to the ground. And corona is a phenomena. I will tell you what corona is in the next slide. And also you need to design the insulators. When you have a tower, the conductor is sitting there, the tower is at the earth's potential or the ground potential because the tower is grounded, right? So to avoid the spark over from the conductor to the tower, you have these insulators which are stacked up so that you have enough number of insulators so to avoid spark over or basically flash over from the conductor to the pole. So these three things you need to worry about. All three aspects require knowledge of electrical discharges. Discharge means when you have a high voltage line, the voltage, that high voltage line might discharge a current through air to the ground, or through the, through the insulator, through the tower, things like that. So these discharges, we can put two types of discharges. One is called partial discharge or partial breakdown. Means the entire gap from say overhead line to the ground is not going to conduct, but it's only halfway or maybe 1/4 way, or even 1/3 way, small amount, or just around the conductor you'll have some discharge, but not all the way to the ground. So there's partial discharge or partial breakdown. The other one is complete breakdown. Means high voltage line, spark over to the ground, complete discharge, or you can have two conductors have breakdown of the air in between and spark over from one to the other. Those are called gap discharges. Now definitions of these two, corona and gap discharges. Corona is an electrical discharge or partial breakdown of air insulation. Air insulation means air, surrounding the conductor, for example, that is occurring with high electric field region, generally in the vicinity of the conducting surface, which is in our case overhead line, the conductor, but sometimes also near insulating surfaces like around insulators, due to ionization processes in the air. We'll define what is ionization, later. Ionization comes from the ions, Gap discharge is really complete discharge, complete breakdown of air insulation between two electrodes separated by a very small gap, known as a micro gap discharge or simply gap discharge, These are basic definitions of these two. One is a complete discharge, the other one is a partial discharge. Corona is a partial discharge. Partial means not complete, it's only limited amount, So here is the physics. I want you to explain to you this because you understand when we go to our high school physics class, we know what is called the Bohr's model of atom. Atom consists of a nucleus which has protons and neutrons in the center, in the core. These are protons and neutrons in the core. And there are several orbits with electrons floating around, floating around the nucleus, right? So we know this theory. So any particle or any atom has this kind of structure. So this is very, I want you to understand clearly this thing because this is very important because many of these definitions later depends on this understanding. So what is going on in the ionization and excitation process is a stable atom has nicely a nucleus with protons and neutrons, and you have same amount of electrons in different orbits and then going through this completely neutral state. So if you excite this atom by impacting with a additional electron, for example, so you excite. Excitation means electron with the atom moves to the higher orbit. Colliding an electron, separate electron, with an atom which is a stable atom can cause two things. One could be excitation, second process could be ionization. What is the difference between excitation and ionization? It depending on the energy impact. So if you bring an electron and excite with an atom, what happens to the excitation? Electron within the atom moves to higher orbit. That means You have several orbits here, from one orbit to maybe another orbit here, all across, but still within this atom, but one orbit to another orbit. That is called excitation. If you look at here the definition of excitation, this is a stable atom, and you collide that with an external electron, so you will have an excited atom plus the electron, the separate extra electron that you have. So this is called excitation. So A is a neutral atom, A star is excited atom, A plus is positive ion, E is the electron, this extra electron. So whereas going back to ionization, what is ionization? So you do the same process, but you have very high energy impact. Then what happens in the electron separates from atom and moves far away from the atom. The atom is here, so the electron, it generates extra electron and then it goes far away. That is what we call space charge. So it's going away from the atom. So if you look at this equation in the ionization, you do the same thing. Stable atom collide with an external electron. That stable atom A becomes A plus, that is a positive ion, plus generates an external electron, plus you already have an external another electron that you already have impacted. So you see two E's here. Okay, this is correct. The reason is your stable atom is giving away one of the electrons and becoming unstable. That becomes a positive ion there. And this extra electron becomes the space charge going into the out of the stable area and coming away. So say this is the conductor and that electron is somewhere here, and that is what is called space charge contributor, that one. So these are the two concepts, excitation and ionization. You need to understand basic concepts. These are physics, in the theory of physics by Bohr's model of atom. So any matter, either conductor or even dust particle, anything is considered to be an atom. Okay, you can number of atoms put it together, any material. So this theory could apply for our conductors as well. Conductor is nothing but bunch of atoms put together in a conductor. So that's the reason why I'm explaining these concepts, which are from the book by Sharma Maruwada on corona. If you want to read more about it, I can provide that reference. So it may not be in the slide, but I can provide that, or you can Google it, Corona in Transmission Systems by Sharma Maruwada. So you can get a book reference and you can read more about it. Another aspect you also need to understand is with the light, absorption of light. So this is just a regular excitation and ionization, but photo excitation and also photo ionization is considered to be with the light, absorption of light, and then energy releasing by absorbing the light. Here, what we are doing is we take a stable atom and then you add some energy, which is light energy, or expose light to conductor, for example. For example, you expose light like sunlight, things like that. Then that becomes the photo excitation. This atom becomes, with the light absorption, A star, which is excited atom. So this is happening because of the light. Here we are bombarding with the atom with an electron. Here we are bombarding the atom with the light. So similarly, photoionization process, what happens is, if your energy, the light energy is a lot, so what happens is then instead of excitation it becomes ionization. That means from this atom you have A plus, which is a positive ion, and an electron is separated and moves away from the atom, and then you also have some more energy. That energy is defined by Planck's constant and then frequency of radiation depending on the absorption of the light. So the amount of light, if you expose to more light, then you can get into ionization. So Excitation, ionization, and photoexcitation, photoionization, these are the concepts. Once you understand these basic concepts, then we can extrapolate these results for corona and transmission lines, because as I said, any matter consists of number of atoms, all that stuff. So another thing that we need to also understand is what is called electron attachment and detachment. That means if you have a stable atom, you add an electron to the existing stable atom, then it could be excited atom plus some energy may be released when you attach. Similarly, you can reverse way, you could do that. You have an excited atom, which is A star, and then add some energy to that, then you can make a stable atom and then release one electron. This is called detachment. Adding electron, detaching electron. So this is the process that goes on. And another way of doing this is recombination. Recombination means you have a positive ion or a positive atom. Atom and ion I'm interchangeably using. Those are the terms you can use. If you have a positive ion, add an electron to that, then you have a neutral or a stable ion plus some energy is released. This energy HV we defined in the previous slide, Planck's constant times the speed of radiation here. Similarly, instead of electron, you use two particles or two atoms. One is a positive atom, another is a negative atom. You add both of them together, positive atom plus the excited atom B, then what happens is both become stable now because of the process A plus and B star, that becomes A plus B. So that is combination. He really negative charged particles and negative ions. So those are combining them with the A plus, the excited ion. So then becomes A plus B. Now, once you understand this, now the discharge. What we say, you have a conductor here. You have an electron that comes out of the conductor because of corona. That electron with in the air, you have air here. Say this is your ground plane here. In the air, you have dust particles, you have a lot of things going on. So this initiating electron will start charge what is called avalanche effect. It will charge the particles either positive or negative, or some more electrons could be generated. So one electron which is initiating one from the conductor here, close to the conductor, because of corona discharge, might start an ionization process which is an avalanche. It's multiplying. Avalanche means multiplying, one to many positive and negative ions, and then also electrons. So this could happen depending on the field around the conductor will also change because of this, these positive and negative ions around the conductor and the other electrons that are generated. The field near the conductor might also change. Now going back to the gap discharge, that means the complete total discharge. If we have a cathode and anode, there are two plates. From cathode all the way to anode, the current will be going through this because of this discharge is complete, discharge development and breakdown. Finally, this air insulation will break down and it will discharge the current from one pole to the other, from cathode to anode in this case. Okay, so this is called the full gap discharge. Okay, for a uniform field electrode arrangement. Uniform field means there's a positive cathode, anode, positive here, cathode, negative. So if you measure with an ammeter, you see a current that is flowing through because of this discharge or breakdown of the air in between those two plates. So again, reiterating the process, what is a breakdown? First of all, excitation of molecules and photon emission occur simultaneously with ionization. We defined what is ionization and excitation. Ionization means the electron will come out of the orbit and go into the air, okay? That electron will have secondary ionization processes, then due to impact of ions or photons play a crucial role in breakdown of the air surrounding the conductor. And as we saw those discharges pictures earlier, so that is the breakdown. Definition of breakdown is secondary ionization process due to impact of ions and photons plays a crucial role in breakdown. In non-uniform fields, which is the conductor, because conductor to plane, conductor is in the air, the plane is at ground potential. The field is not uniform because the conductor, say HVDC conductor, is a positive or negative pole, right? The ground is at zero potential. The field is not uniform. The field at positive conductor is very high. At the ground level, almost close to zero, right? So it's non-uniform. Partial breakdown or corona occurs. So most of the places when you're talking about conductors, you have a corona, not complete gap discharge that occurs. Because if complete gap discharge occurs means your design is wrong. Now if you have a track going underneath the line, you might have a complete breakdown or that might happen, but that is a wrong design. So you have to design such that the highest track, the height of the track you should consider that is going underneath the line should not cause the air breakdown from the conductor to the top of the track point. Okay, that's important to note. And John will talk more about those standards and how many, the distance wise, what are the standards we use, and also you have to have extra margin so that if something happens, you still don't have a breakdown. The corona might occur, but not breakdown of the entire air gap. Now coming back to DC corona models, like the DC negative corona model, negative pole, think of a negative pole here, negative conductor with a minus here. The avalanche occurs, as I told you. First of all, the conductors at certain voltage level, they are fine. They don't emit any electrons. As you keep increasing the voltage to certain values, your voltage is getting higher. So you start feeling this kind of discharge coming in the air. One way of seeing the discharge is the hum noise. You see the noise like that. Like in a substation transformers, they make noise too. But even in lines, when you have a corona activity, you see this hum noise. That means this is what is happening. As we discussed, one electron comes out and then starts generating these other ions, positive, negative and all. In the case of negative conductor, mostly negative ions will be coming. Your ground plane, which is ground, you don't have a complete breakdown. So there is a boundary around the conductor. That's where the space charge is limited here. Okay, but in the what is called in the secondary initially it starts with that. Some of them will stay around the conductor, but some of them will separate and go into the space. And ultimately they come closer to the ground. Some might be deposited on the particles or whatever the subjects, trees, whatever you have. So this is how this whole operation works. The negative DC corona models with the negative ions. What is the impact of these space charge that is coming out of from the conductor is, if you look at uniform original field distribution, you have electric field E1 at the conductor. This is where the conductor is. So your ground is somewhere here, or the ground plane. E1 in the conductor is constant until the surface of the conductor. Then as you are going away from the conductor, so this is the center of the conductor, surface of the conductor, right? So as you are going away, the field will go down because you are far away, and the field eventually will have some lowest value which is allowed at the ground level, or sometimes you have depending on your standards, you have 5 meters above the ground. What is the field level you need to have electric field? So this is the blue curve is without any space charge issues. But in the case of DC, because of these space charges that we see in the air, the field gets distorted. Because the field gets distorted, the electric field could be higher there, and then again it could be lower here. So depending on how these space charges are distributed, it's a nonlinear phenomenon. Because of the wind, the space charges are blown out, and then depending on what kind of pollution you have in the air, and it is also the corona depends on this surface of the conductor. You have some kind of bugs stuck on the conductor, you may have more corona, because you have those points, the sharp points on the conductor will create corona issues. So more details you will see on that tomorrow. Just to give you types of things that you see in corona for the negative DC, basically you need to remember these three: Trichel pulse, negative glow, negative streamer. These are the three types you will see in a negative DC corona modes. So those three are shown here pictorially. Trichel pulse means it's like a pulse, it comes in a pulse. Glow is more like, you see the light. Whereas the third one, streamer, is like a big, long discharge. So these are all three types of partial discharges that are defined by three different names because of the shapes. For DC corona, negative DC pole, okay, this is the type of things you see on a DC pole. Similarly, for positive pole, if you take a positive conductor, you still have similar thing, only thing you have more positive ions here coming out and spreading off the burst of corona because of the wind and all that, they keep going. And then again your electric field will distort, like we discussed earlier, because of the space charges. Say your dotted line, your uniform field, okay, from the surface of the conductor all the way to the ground, but it will be distorted because of these positive ions you have in the air. So looking at the, again, types of positive DC corona modes. For a positive pole, the positive glow and breakdown streamer, these are two types. So those are shown here, onset streamer and a glow. This is the type of things, the corona you see. We have what is called corona measuring cameras in North America, and also a lot of utilities use that, and there are different equipment to measure these glows. You may not be seen with a naked eye, but you can see them using cameras. Now comparing to AC, what happens with the AC? AC has two cycles, right? Half cycle, positive half cycle, and a negative half cycle, right? During, for different voltage levels shown here, as I said, as we keep increasing the voltage, generally the breakdown of the air happens at the peak of the voltage. So here the positive side, complete breakdown here happens here as you go up to 106 kV in this case, in this experiment they did. The positive side here, whereas the negative pole are not pole here, negative half cycle, because this is AC here. Positive half cycle, negative half cycle. Negative half cycle, you see more glow here, as you see here. So for different voltages, these are AC voltages. So this is how you compare with AC corona versus DC corona. So you'll have more numbers, which one is bad and all that tomorrow. But this is how the whole thing works. Gap discharges, we talked about corona is a partial discharge, right? It doesn't complete the path from all the way conductor to the ground. But whereas gap discharge could happen in your equipment, gap discharge could be like if you have an air gap, it might break down the air in the gap and then completely discuss, this is at a potential, it can discharge a current. The current could be drawn like very steep, small nanosecond to microsecond time frame, it goes up and suddenly goes down, okay? So this is how this current could be measured, going through the gap, this typical current pulse produced. And I have some numbers for the rise time and fall time and all that stuff later in the slides. For your information, I'm going to go through them very quickly. Generally, gap discharges happens between metallic hardware parts of transmission and distribution lines. These gap discharges will happen. and between metallic and insulating surfaces. And on the surface of polluted insulators also you can have gap discharge. So whereas corona generally happens around the conductors. Similar to excitation and ionization concepts are very similar. I won't go through these much. For the gap discharges also you have this, but very similar notation, excitation, photo emission and all that. In the interest of time I won't go through that. You can read them again. These are basically the nitrogen molecules that are released. So light emission from discharges. When we have a discharge, you have light that is coming out. Whether it is a corona or a gap discharge, you have a light emission. So the light emission is in the ultraviolet range. See, stronger emissions having wavelength in the range of 300 nanometers to 500 nanometers. It's defined as the stronger emissions. Weaker emissions 80 nanometers to 200 nanometers. So some information about different types of gases that are released when you have these discharges, either gap discharge or corona discharge. So again, more details given in the photo absorption area. Even the oxygen modules are there. So again, in the interest of time, I won't go through these details. You can read them through the book if you are more interested. This is important. Another thing is when you have a corona discharge, radiation happens. Radiation here, radioactive intensity versus the wavelength is given here. So again, corona discharge emissions in the air, 210 to 500 nanometers. So this is the radiation aspect. And the audible noise is another aspect. Just to compare the radiation from sun versus the radiation that happens in the conductors, that is given here, the numbers you could compare. So this is 100 times. You see in the air the radiation from corona discharge. So these are the numbers for the solar, for the sun, the radiation numbers and the wavelength. Similar numbers given there. Again, this is corona, as I told you, when you are running at a lower voltage, you don't have a corona issue. As you keep increasing the voltage, either the DC voltage for the DC lines or the AC voltage for AC lines, at one point corona starts happening. It's called corona onset voltage or onset gradient. Is defined by this equation EC with a different number of constants. These are all derived. In the literature you see those constants are given here. K, for example, you could substitute 0.30. E0 is 30 kV per centimeter. All this again, more details come from John's presentation tomorrow, so I don't want to spend too much. This is the equation that determines when corona starts, inception, onset gradient, corona onset gradient. So this is also very important when you design your line. So you need to use your configuration of the conductor and calculate when the corona starts happening and limit your voltages, operating voltages based on these limits. So again, it also depends on your conductor radius in centimeters, conductor surface gradient, irregularity factor, and all these things influence when corona discharge starts around either AC conductors or DC conductor. This is called Peake's formula. Peake is the person, I guess, who invented this. So just let's talk a little bit in terms of what are the impacts of this corona or partial discharge. Corona is coming on top of the conductor, around the conductor, right? It's discharging some current. So that means when the current is discharged, you have a loss. It's called power loss or corona loss. That is important to note because that is taking away some real power that is transferred on the line. Not only the power loss, but it is also causing radio interference. If you have a radio communication lines or that has impact. In general, we call it electromagnetic interference, but that could be radio or television interference. Another issue is the audible noise, the hum noise, and the other issue is the different things like ozone could produce NOx. All these things could come out of a corona. When you have both for AC and DC lines, these are all common. For DC lines, we have these space charge issues. We talked about positive pole emitting positive ions, negative pole negative ions. Those will have impact because they pollute the environment around the conductor, and then the electric fields will distort. So for DC lines, you have these space charge effects, which will change the electric field configuration around the DC lines. For example, AC, different types of AC conductors. You have the advantage with AC is because it's positive and negative going, every half cycle, the ions are coming out, going back in. So it's not, the space charge is not going into the air. Whereas in the case of DC, positive ions will come out of the positive pole, negative ions come out of negative pole. Now let's talk about monopolar line, which is also considered as unipolar. Uni is one, mono is one. So some people call unipolar lines versus bipolar lines. What happens to this if it happens to corona? So take unipolar line, a positive pole. You have a positive ions coming out because of the corona, filling the gap all around the conductor. This is the conductor, okay? Some may go up, some may go down, some may finally deposit on the floor, on the trees or animals, whatever. So this is all the flow, everything is positively charged. Whereas if you have two poles, positive pole and a negative pole, in between this positive pole and negative pole, the negative ions come this way, positive ions come this way, they neutralize each other. This is a bipolar region, negative region here, positive region. The bipolar region is somewhere here in between these two poles. So you have distorted fields now everywhere. So this is what happens with the bipolar line. Now the impact of this corona on the radio interference is shown here. The radio interference with the DC positive, corona current pulse trains are injected into conductors. So the DC positive pulses are shown with respect